Good afternoon, all participants.
Good afternoon.
Good
Good
afternoon,
afternoon.
sir.
Yes, okay.
Okay.
So, welcome you all on day 6 of FDP on next generation artificial intelligence, machine learning, and Internet of Things, organized by Department of Electronics and Communication Engineering of VVP Engineering College, Rajkot, Gujarat. I, Jignesh Joshi, and Dr. Dipesh Kamdar, on behalf of department, welcome you all. And we start our session 1. Let me introduce and invite Dr. Dipesh Panchal sir. Welcome Dipesh Panchal sir.
Yeah, thank you. Thank you, sir.
Yes, let me introduce Dr. Dipesh Panchal sir. Dr. Dipesh Panchal sir is working as an ASIC physical design engineer in E-Infochips Limited, Ahmedabad. He received a BE degree in Electronics and Communication from South Gujarat University and MTech and PhD degree in VLSI design from Nirma University, Ahmedabad. He has 15 plus years of teaching experience. His expertise is in analog and mixed signal design, VLSI physical design, semiconductor device modeling and physics, low power VLSI design, digital VLSI design, and high performance VLSI design. He has expertise in Mentor graphics, T-Spice, H-Spice, Cadence Encounter, Microwin, Visual TCAD, Synopsys EDA tools too. He filed Indian patent on design and simulation of ultra low voltage amplifier for digital hearing aid. He has conducted 5+ workshops in the area of VLSI design. He completed 5+ major and minor projects from Rajkot and Nirma University. He has guided 30+ PG dissertations. He also guided 150+ UG level projects. He has published 15+ research paper in national and international journal conferences. Welcome, sir.
Yeah. Thank you, sir.
You are having experience as academics as well as industry. So you better know the audience which is in front of you from the all India. Actually, 240 to 50 participants will be there within some 15-20 minutes. But just to finish the all sessions in time, let us start with your presentations.
Yeah, thank you, Jignesh, sir. My screen is visible.
Yes, sir.
Yes, sir.
Okay. So just little quick. I may know the background of the audience. Hello.
Yes, sir. Now you can continue.
Audience. Yeah, audience from which streams? Maybe electronics and communications, maybe computer science, or mix of themes.
A mix of teams. Most of them are from computer science and electronics and communication, but few of them are from other streams also.
Okay. Okay, so let's begin our day with the new emerging technology that we call as a quantum AI, okay, artificial intelligence. So IDPS Panchal working as a design engineer at the E-Infochips, ASIC design engineer. So my more towards the hardware levels, designing the physical layouts and everything with the complex circuits. So my interest towards this embedded domains as well as AI and the machine learning as well to know the more deep. So I'm not an expert in this field, but yes, I have interest to learn and yes, to share the knowledge with you all. So today I am going to talk about the quantum AI, artificial intelligence. I hope my screen is changing, right?
Yes, sir.
Yeah. So these are the content of presentation. We'll start with the introductions. Then we have a why we are looking this new emerging technology that is quantum AI. So we are building some motivation behind that with the help of traditional computations, then quantum computations, then role of AI as well as generative AI, and then we have a quantum AI and on which platform we are using. Okay, finally, whatever software we are developing, algorithms we are developing, finally, we have to use them with the help of hardware. So we have quantum cellular automa that provides this facility. So we'll discuss how it is work with the complex algorithms, and then we'll look about the applications of quantum AI, followed by conclusions and references. Okay, so we all aware with the computations. So recently at our e-info chip, we started to work on one of the cell phone that has a 25 cameras. Mostly max we have 4 cameras in our cell phone, but customer demands that we need more and more cameras to take the more images and to perform the complex computations with the help of every angles of the images. So that's it says that in upcoming days, the competitions or to take the clarities of that all the angle views and the computational complexities are very large. So we have a competition speed, okay, at which rate we are doing the processing that with the help of our process data. So we have terminology like we have millions of instruction per second. So whenever we go to buy any systems, we are first looking this millions of instruction per seconds. Okay, that we call as a computational speed. So early days in 1980s, 1999, this is a major requirements that how fast we can do the computations. So we are normally look for this kind of specifications from our systems or any CPUs or any GPUs. But once we looking for a higher and higher speed, everything not come with the free of times. We have to pay something. Okay, we have to also pay if you have to look for a higher speed. Definitely, we have to pay money for some other benefits. For example, in this case, after 1990s, 2000 onwards, when the speed achieves at the higher numbers, major drawbacks comes into the power dissipation. So we have to pay more and more money where we can save the power dissipation. So whenever, if you have observed that whenever we open our CPU, okay, at the SMPS or on the microprocessor, we find the fan that provides the cooling, as well as at the circuit level we have many power management units start from specifications to final layout. So in between there are many methodologies we add for to save the power. So our wish to that not only the higher speed but at the same time that with the low power dissipations we can achieve our goals. So speed and power, that's trade-offs we need to handle. So computational speed that of course we can achieve as per our desire, but at the same time, power is also the concerns. High performance computing, that is also the buzzword on the desk that day, that ability to process the data and perform many complex calculations at the higher speed, at the mega millions of instructions per second. So if you recall that our cell phone is not only to do the one task. If it's not only just to talk with someone, there are many features, are there additional features, additional complex algorithms, and the many image processings are there. Okay, as I said, 27 cameras on the single cell phone, so you can imagine the speed and the computation power. So in that case, our whatever logic we are designing, that is our transistor level logic, that is our gate level logic, is also very complex. So whatever circuits available to implement that task is very complex. So in that case, my system perform the multiple tasks. So with that sense, in that we can say that we are reached to the very small size of device, and on the device we are performing the complex task. So the circuits are complex nowadays, and of course we to do all the processing we have a higher processor speed that measure how many cycles that single CPU can execute per second. So these are the computational point of view we are talking at present. So as I said that the single cell phone is not for one purpose. There are many additional functions to play a game also and many other additional features. So in that case, complex circuits are required. So once the circuit is complex, definitely each and every transistor takes few fraction of time to do the processing. So in that sense, we are deciding the speed of our systems. So computational speed of any gadgets, any instruments is very useful, and key performance metric that with the help of many algorithms we can perform the task. For example, recently last year in 2024 we designed one the network chip for the Google. In that case, where huge computations were required and the circuit is too complex, where millions of transistors are there. So whenever any client requirement is coming, same way for this 27 camera cell phone, any client requirement is coming, we are not straightforward start layout design. So there are in between many steps we are following, and finally we reach to the layout. Very first job, whenever client says, I want to design this XYZ network chip or network processor. So in that case, our first goal, we have to divide our entire customer requirements into the small modules, small blocks. So there is a millions and trillions of transistors are there in a circuit, so we cannot start layout designing at the one place. We need to form the different modules, different blocks of entire chip. So there is a complex algorithms are there that gives the very optimum solutions of each and every areas. How I can divide entire SoC into the small blocks. So in that sense, I can implement individual blocks separately and then later on I can combine. So that is more efficient, and for that there are complex algorithms are used. That is KL algorithms are there, FM algorithms are there, and that used to perform this kind of task. So for that, the computational speeds for the CPU or GPU is requirements. So for example, the example of computational task, that is our very popular mathematical computations as well as sorting algorithms. Example of computational systems, we can say, as I said, cell phone or GPU, CPU, X-ray machines, calculators, and banking systems. These are the computational system where on the hardware, we have algorithms are there which are very complex in nature that need to perform the complex tasks. So for that, we are not, it's not like that. If I want to do the some partitionings, if I want to take some X-ray image or some scientific calculations, I don't need to wait for a week or a month. Within a fraction of seconds or in a hours, we'll get the results based on this high efficient designs. And in early days, that improvements that is use of increase the memory size or increase the solid state device. That was the original solution. But nowadays, many options are there for these traditional computational competitions. So this is the image shows that from early 1990s to the 2025, where these all years on the x-axis and the y-axis, we have calculations per second. So 10 is to starting from 10 is to minus 4 to 10 is to 16 on a y-axis. Keep my cursor in on state. Yeah. So start from 10 is to minus 10 is to 16, that computations per seconds as respective with the years. So we can imagine that mouse brain computation speed, and now almost we touch with the human brain speed. So we started with the devices like electromechanical device, then it is early 1994, it is replaced with the solid state device. Then vacuum tube came into the pictures, and in 1961 that first transistor was developed for do this all computations. And finally, we got the integrated circuits. Okay, that is a form of the ICs that we call as a processor, motherboard, on the mother sitting CPU on that. Yes, ICs are sitting that performs the multiple tasks. So that in that sense, if we have a very complex system, complex algorithms, that computational speed to be high, and we almost reach to the speed of the human brain. Nowadays, you cannot imagine that we are doing the research that if you want to connect the if you know the wiring, okay, so in integrated circuit also there is a wiring. So we are not nowadays using the electrical wire, because if you are using the electrical wire, it take long time to transfer the data. So in that case, we are using the optical communications. Okay, optical medium as a communications to transfer the data from one place to other place. And also we are using the RF medium to transfer the data from one place to other place for 2 pin of the ICs or do the connections. So in that case, we can very quickly transfer the data within the IC as well as external devices. There are many other options that we can approach apart from our electrical wirings. So in every sense, we need to minimize the glitch and the delay. So in the shorter time, in a very less computational speed, we get the outputs. So computation is a major challenges because of complex algorithm need to be implemented on the complex hardware, because in a small gadgets we require many functionality. As I said, the cell phone is a good example. So the computations we can achieve with our classical computations. Okay, computations we can also achieve with the quantum computings, which is the high speed computings, and we add the AI features, AI intelligence feature, artificial intelligence features with that computations, so we can do the better prediction as well. So computations as classified that we can perform with the classical computations that normally we are doing, okay, in our office, in our college, like that. With the high speed and high complex algorithms, we have quantum computings, and with the additional feature of artificial intelligence. All three are combined together that emerge the block of quantum AI. All three blocks, that is classical computations, that is our traditional computations we are doing, adding of more high-speed quantum computings with the different devices that we'll talk later on, and the features of AI intelligence. And that gives our model of quantum AI. So in the next few times we are discussing about this all the classical computations, quantum computings, and artificial intelligence. There is a advantages and disadvantages, and why we need to move towards the quantum AI. And finally, we also discuss the what are the hardware challenges, because at the end of the day, everything need to be implemented, everything to be done on a hardware, so we can perform the task. So we'll see that how we can take the challenges of the hardware designs. So high performance computing was a original trends. Okay, and nowadays we have artificial intelligence also, and more advanced is a generative AI, that the significance driving force to drive the complex problems. It has its unique capacity and merits and demerits, and almost they are used to provide the better solutions in the least time, and it gives the solution for the complex algorithm as well. In the play with that traditional, we have a addition of quantum computings, that the additional features to improve the speed of our computations. Fundamentally, it is more and less or more equal to traditional computing, but with the quantum computings, we at the 2 times, 4 times, 8 times the higher speeds. So this is a typical architecture of our high performance computing, where we have multi-core processor is there. Then we have a HPC, high performance computer, single node is there, which includes all possible types of multi-core processors. And this is all clusters are there that we call as HPC cluster with form. Normally, this kind of HPC architectures need to follow at the networking or net cloud computing or networking chips or network or data centers, huge data centers like Google. So they follow this kind of architecture for computations. Classical computing as we all doing normally our day-to-day life, that is our binary computations. So that is very traditional approach, and we are giving the inputs and we are getting the outputs. So we apply the bit 0 and 1, either logic 0 and logic 1, and that is our traditional computing. Let's say if I say all of you know the digital gates, AND gate, OR gate, and if you say that 2 bits, we have a 4 possible combinations, and that all 4 possible combinations, I have a output either logic 0 or logic 1. So in that case, that kind of computations that we call in a category of classical computings, where only bit 0 or bit 1 is used to give the outputs. So it's our day-to-day solutions. It's very deterministic approach, and yes, why it is deterministic approach? That yes, we know that if you apply this kind of inputs, my expected output is look like this. So it's a very deterministic approach to follow as a traditional computings. So it's a binary course, 0 and 1, as I said that plays with the zeros and ones, and it's a deterministic approach. And most of the times in digital, yes, with the help of K-maps and all that predictions, we can better know that yes, this can be the probable output. As the speed is concerned, that is a classical competence that provides trillions of operations per second, where the switching of these tiny devices. So whenever we apply 0 and 1, there is a mechanism in our hardware. There are many challenges that, because as I said, millions and millions of transistors are there. That number of transistor, I have to make it on and make it off. In that case, there is a propagation delay. So that delay we need to count for each and every switching. And of course, as I said, in a HPC, high performance computing, there is a parallel processing. Okay, there is a parallel processing, and that gives the improvement in speed. So in many cases, let me just give the brief of these parallelisms. All of you are with the digital gate, right? Because in computer also we have a gate mechanisms. So let's say I'm asking you that I need the 4 input AND gates. So your first answer is look like this: 4 input AND gates, right? I hope computers maybe learn that BTech maybe in the first year, or nowadays digital gates are also in 11, 12 standard in science. So if I ask that 4 input AND gate, something like this. But if I'm saying that use only 2 input AND gate and get the function y equal to ABCD, can anyone think what could be the approach? This is at the device level. Inputs are ABCD. So if I'm saying that I have to use only 2 input AND gate, not 4 input AND gate, what could be your approach? So your A and B's are the input here. And again, you have combined this A and B with one more input, let's say C. So now here my output is ABC. And here again, I'm taking the D input, and here I'm combining A, B, C, D. This is my output of A into B into C into D, right? Is it fine to understand this? Can anyone reply? So this is the use of 2 input AND gate. Now, if I'm saying that I can also design like this, again, my condition that I have to use 2 input AND gates. So again, I have 2 inputs like this. And again, I am going to use one more AND gates, and I combine this AB and CD with one more AND gate, and I will get the output again ABCD. So I have a 2 approach. This approach also and this approach also. So which one is more faster to get the output? Output is ABCD. This number 1 or number 2? which logic gives the more quick output, very fast
Number
output.
2, sir.
Yeah, so there is a parallel processing of the inputs. So this is at the gate level. Same we are doing at the core level, parallel processing at the core. So many GPUs, CPUs are running at the core are running at the same time to get the quick outputs. So parallel processing approach now very popular at every abstractions level in a designs. If you start with the circuit or gate levels, it reach up to the system level as well. And of course, as I said, finally, everything we need to handle to the silicon based designs. Finally, we need to use the hardware on that this everything is running perfectly as per our expectations. And yes, of course, external memories are there. Is that every system as a classical CPU as a external memories are required towards the storage purpose. So little bit quick history of the classical computers. As I said, that's a bits operation. There is either one or zeros that serves in the purpose of in our laptops, in our smartphone, as well as in a supercomputers. And as a combinational or sequential approach, as well as we apply the inputs in a fraction of seconds, we'll get the outputs. So this everything need to be translated into the hardware. It was started in early 19s with the help of integrated circuits, and nowadays we are switching towards yes, so switching towards this quantum computing as well because everything is not possible with the limited devices. So we need to change our device approach also. Cannot use the same device all time for all purpose. So nowadays, that research is there towards going towards the quantum devices. So ICs that yes, and with the help of ICs, we can develop the processor and many classical computers. So yes, physical limitations that probably you all know the Jordan Murray's from the Intel. Yeah, that's a very well known. So Jordan Murray says that every 18 months you will get the new processor, new system, new silicons in your hand that is more com- higher computational speed with the good computational power. So that's why you can see that after 2 years or after 15 months, a new cells come to the market, new model of the cell phones coming in the market with the more additional features. But that is a limited capacity that everything we cannot do on the single or in the same types of system design approach. So in that case, let's say if we are working in our industries right now, we are working at the very small level of the device. Probably the terminology, maybe if you are in electronics, you know that terminology we call as a technology node. So that is Moore's law says that started with 5 micrometers, then 3 micrometers, 1 micrometers, then 180 nanometers. Nowadays we are working on the 3 nanometer, very small size device, but we can reach up to 1.2 and maybe 1 nanometer as well in the future. But what could be the case below the 1 nanometers? What is the device? Which device we need to use? So the approach is the quantum mechanisms. So we follow that single electron approach to design our quantum computing as well as high processing GPUs. So this is all Moore's laws, and there is some limited capacity that we cannot scale our device for higher computations. We will below the 1 nanometers. So in that sense, we need to change the device structure also. So everything we are smaller size, you can easily carry our cell phone in our pocket, laptop in our small bag. That is because only because of small size device, smaller area device. If my area utilization is smaller, then I can achieve the higher speed. Okay. So that is the approach we are using in industry also. Whenever any client requirement is coming, initially, he defined that yes, I require my entire system network chip on this by this or this micrometer by this micrometer scale, not in a big size. So it has some fixed dimensions. It has some fixed dimensions defined by the clients that yes, these are the dimensions required. On that, only need to define the entire systems. Okay? Entire complex system need to be built. So whenever externally you develop any software, any algorithm, complex algorithm, that need to be run on only on this square of the chip, final hardware. So that's hardware is smaller in less time, all the computations can be performed. So my computational speed becomes higher. So this is very challenging nowadays because, as I said, we are working at the 3 nanometer, very smaller size of the device. So in that case, I have to take care for that small device. If any external temperature is changed and any physical quantity is changed, there's a huge impact on that device. It is similar look like a baby. So baby very small, like 1 month, 2 months, 5 months, 1 year, almost 2 years. There are many possibilities that disease are happen. Some environmental is change, that cough and everything need to go with the doctor and like multiple times. So same way in a chip also, if it is small in size, that external environment affect a lot. So we need to take care in designing with every aspects to perform that computational functions. So chip becomes smaller and smaller to perform the many tasks in a less interval of time. Of course, my system is smaller, my device is smaller. It is not like that. If I am transferring the zero from this end to X to Y, okay, from line X to line Y, I am transferring my logic zero. It should not be transferred from X to Z. Okay, I have to make sure that the direction of my signal should not be diverted from original path X to Y. So if it is X to Z, then that could be the effect of called the tunneling. Okay, so that could be the effect of tunneling. So I have to make sure that in a smaller size, smaller regions, the direction of all the signal remain as it is, as what defined in a system level or in algorithms. So that need to be there physical limitations. Second one, that is of classical computing, undergoes with this all the limitation, that explosions of the complex data and their optimization challenges. So like the big data systems, complex data systems, we cannot able to develop with only knowledge of logic 0 and logic 1. So in that case, many optimization problems like such as a deep neural network or maybe high dimension data that need to be used in such a way that I can play with that complex algorithms as well. So complex data cannot if efficiently computate with our traditional computations. So that comes in a category where classical computing, that is with the use of zeros and use of logic 1, that not longer to be achieved. Okay. So that is our limitations for logic 0 as well as logic 1. Now, second one is our quantum computing. So this is the some part has some advantages, some part has some disadvantages also. So as I said initially, all three combined together, that the traditional computing, quantum computing, and the features of AI, that all three combined together, that gives a new area that we call as a quantum AI. That is a topic of discussion for today. So second one is our quantum computing. So as I said that we require higher computational speed, and that is possible. That is possible with that is not possible if you have a smaller area. So if I am talking at the device level, everyone know the transistors, maybe computers, faculties has less knowledge. But if it is a electronics and communication side, yes, they know well about the transistors. So this I am talking. So this I am talking over here. This is the just pictorial 2D structure of the transistor. This is my three terminal source, drains, and the gates. So higher speed, it means our electrons are traveling from source to drain. So if this distance is smaller, what I am talking 3 nanometer right now, we are working on 3 nanometer. It means this 3 nanometer distance between source and drain, just 3 nanometer. Okay. So electrons require very less time to travel from here to here. That means my device speed is larger. So whatever complex algorithms I develop externally that can be dumped on this kind of device, and my computational speed of the GPU or CPU becomes larger. So 3 nanometers, yes, we started with 180 nanometer, 1 micrometers. Now we reach up to the 3 nanometers. Again, we can go up to 2 nanometers in upcoming days, and by 2030, we can reach up to the 1 nanometer as well. Okay, so this distance between these two terminal, okay, that is the source and drain, that is only 1 nanometer. You can imagine that speed of our traditional competitions, all for the traditional competitions. That is with the logic 0 and logic 1. But what could be the case less than 1 nanometer? What kind of technologies are there? So the answer for this is a quantum computing. Answer for this is a quantum computing. So there is a approach to use, systematic approach we need to use. We have to play with the particles of the materials in such a way that we can achieve the desired speeds. So we have building blocks for the major computing system. Normally we call as a bits, logic 0 and logic 1 we call as a bits. But here with the quantum computings, we have to call as a qubits, combination of the bits. Okay. So that terminology is not individual bit, that is combination of bit. For example, in traditional one, we are defining logic 0 with 0 and logic 1 with 1. But in the quantum computings, logic 0 either can, yes, someone having carry, or you can mute yourself. Logic 0 we can represent with 1 or 0, as well as logic 1 we can represent with 1 or 0. That is 4 bits we can represent, that is qubits. That representation is a qubits for the quantum computing. So that is a major challenge, is that that phenomena, that is quantum phenomena, that like superpositions principles, entanglement principles, that can be applied to follow this combination of all 4 bits. Because I have previously I have only 0 and 1, but now I have all possibilities. So superposition principles as well as entanglement principle we need to apply for the logic designs. And of course, if we have more bits, we can design our system with the very fast and efficient way. So as compared to the our conventional system that makes our system very fast with the help of the machine learning and other machine learning approach. So this is our classical computers. As I said, first state at a time, that is either 0 or either 1. Let me put the pointer. Yeah. So one state at a time, that is 0, 0, 0, that is bits, or either 1, 1, 1. All bits are independent of each other. While in case of quantum computing, either 0 or either 1, both way we can possible. That's a concept we call as a qubits. So these are combined state together. All bits are combined state together. So here only we have one state at a time, but in this case we have many states at a time. So in that case, I have to use the superposition principles. I have to use enlargements as well as interface between 2 bits. That is also play the role to get the final result in my systems. So it's a different from classical approach. So up to 1 micrometer, up to 1.2 nanometer, I can go for the classical computers, but before that, I less than 1 nanometers, definitely I have to change my device also. So this kind of structure normally called the single electrons. Okay, you have to play everything with the single electrons, not with the multiple ones. So superpositions and quantum informations like that. So as I said that 50%, if arrow is upward like that, we can say that kind of logic is 0. And 80%, 85% if arrow is down, we can say that can be the logic 1. So that single 0 represent with logic 0 also, as well as logic 1 also. That is give the qubits. Quantum entanglement also that plays the role in which directions my electrons are moving. This is the case for single electrons, either in the left side, either in the right side. So in which direction it is moving. If it is moving towards this side, that can be identified logic 0. If this is moving towards the bottom side, can be identified logic 1. So movement of single electrons that also play the roles in the qubits that determines in which directions my electrons are travel. So that can be identified as a logic levels. So in terms of, let's say it is 0 0, that we can call as a 25% of level, that is 0 0. If it is only 10% of level of traveling, we call as a 0 and 1. If it is highest one, we call as a 1 0, and it is 25%, we call as a 1 1. So if there are n qubits, all possible distributions, probability of distribution is 2 to n states. So all possible distributions are there in the quantums. Interface between the qubits are also there. So we have a logic 0, we have logic 1, again logic 0. So we combine this all waves that we call as quantum waves. We combine together something like this, and we form the overall wave function for our designs. And based on that, we calculate, this is for 3 bits, A, B, C. Based on that, we calculate the probability distribution functions, PDF. Okay. And we can say, yes, if this percentage is there, it is a 0 0. If it is a 15%, it is 0 0 1. Let's say it is a 25%, it is 1 0 1. So more number of bits we can represent at a time. So why this approach is there? Multiple bits approach is there because, as I said, that device is very small nowadays. So smaller the area, in very less time we can perform the task. Any computationals we can achieve very fast if the area is smaller. So if area is already smaller, so why not we need to add the number of bits only to, instead of representing either 0 or 1, we can represent with both 0 0 as well as 0 1. So in that case, if number of bits are there, more transistor we can accommodate in a smaller area. So our computational speed to be increased. So that approach we are applying in a quantum computings. Interference of the signals also there. So sometime it is a constructive interference, and in some time it is a destructive interference. So it's a constructive interference, just we are following the path like this. So these two waveforms are added, look like this. And it is a destructive interference, we are neglecting the opposite movement of the waveform. So if this is the waveform, one waveform, this is opposite waveforms, okay, orange and green. So that distractions we are removing, so that signal remain as it is. So nature of signals, nature of the waves, that also play the role of the traveling of the atoms. Next, we have a quantum algorithms. So once we develop this kind of hardware for efficient or large calculations, what kind of algorithms we are going to implement? So there are n number of algorithms are there. Few of them are listed in this slide. Like Ditch algorithm, Bayesian algorithm, Siemens quantum phase sorts algorithms. This is fraction algorithms. Is that said, let's say we have multiplication of two numbers, we got some results. Okay, very easy calculations. And then if you want to find the fraction of this large answer, then it's difficult with the help of traditional computing. So with this large number is there in digit of 10, digit of 5, something like that. So fraction of that numbers calculation is not easy task. So in that case, we have to take the help of quantum computings. So factorizations of with n digits, if it is there, then we can easily calculate with smaller fractions. But it is a complex 9, 10, that number of fraction of large number we need to find, then its task is very difficult. So we have to take the help of this qubits. In that case, that will get the efficient results. So here is a quick comparison. So this side, left side, everything good for quantum computings. On right side, I have a classical computings. So number 1 point straightforward says that I have to use qubits. I have to use either on or off, 0 or 1. Okay. Very big problem here when there is a power increases exponentially in this case. Okay. While here that remains 1-to-1 relations. That is a linear relations of the power dissipation. Of course, I have to save the power in the both case by additional logic or additional hardware or additional algorithms. So that's why if you go in market for purchasing the cell phone, we are always also looking the battery capacity. Same way for laptop, we are looking how much MAPH that will be work. That is 3300 or more than MAPH, we need to pay more money. That means additional hardware is there in a system that save my power. Also, whenever we talk on our cell phone, when we keep our cell phone nearer to our ear, the display becomes off. So there is a power management unit is available that saves the power because we know we are not going to see the screen of the cell phone when we are talking. So during that interval of time, my display becomes off. So that is a use of additional power management circuits. So that improves the performance. Yes, here low error rates in the case of only 0 and 1. But here, if I playing with the multiple bits, there are chances of error is also very high. And its applications wise it's suited for the classical computers, but for here it is used for supercomputers and for simulation analysis and any purpose. So we'll see the application of quantum computing. IBM as well as Google quantum computers are available, so that is used for quantum simulations. So heavily or materials diagnostics is possible with the help of this quantum computing. If you want to identify in the chemical or in biological engineering, if you have some manipulations or of the particle of subatomic particles that we can easily identify with the help of this quantum simulations. So for that purpose, we are using this quantum computers. Also is a simple example to give the coloring of any graph. So graph theory is a very popular approach in engineering. So if you want to distribute the millions of the nodes in a graph with different color, so two consecutive colors are not become same. In that case, also this kind of quantum computing approach is there that gives the result in a less time. Behind the quantum computers, there are complexity analysis is there. So if you remember, this complexity is based on the complexity of algorithms. So we have a polynomials complexity, we have a non-polynomial complexities. So polynomial as well as non-polynomial complexity, this is our traditional computational approach that follows this complexity. But combination of n and p, that is our BQP that we call as a BQP complexity that follows our quantum computing algorithms. So in a how much runtime is required. Okay, this complexity means how much runtime is required to give the solution of that XYZ algorithms. So polynomial algorithms, non-polynomial algorithms, as well as BQP. So BQP is a very standard approach to use this, that is bounded error quantum polynomial times. So it gives the mathematical representation that within this interval of time, your results are available apart from your polynomial as well as non-polynomial case. So BQPs follow, there's a mathematical approach to calculate the runtime for systems. Yes, so this is very important slide, and it says that what investment done by in different countries in the field of quantum computing. So numbers are in US dollar, in billions or in millions. We at India, we are at the 73 billions. Okay, approximate US in USD 1 billion investment India did in the field of the research of the quantum computing. So nowadays, if you see the IEEE transaction also, they have started giving the research on the quantum computing. The softwares are available where you can design the quantum systems. Australia is doing too much advancements in a quantum computing. So we have a deal with one of the University of Australia that they are giving the research guidance in a field of quantum computing to use the software and how to how to realize the high computational system with the help of software, change the materials, change the algorithms like that. Next and third phase is our artificial intelligence. So yes, whatever complex algorithms we written and we dump on our hardware also, but what could be the next level? So next level is always the prediction, and that we call as a artificial intelligence. So something we need to expect from our this all complex task that in that the task becomes very easy. So with the help of predictions. So that may be with the help of machine learning as well as deep learning approach. So artificial intelligence has come into the picture that yes, the help of robotic processing or with the help of machine learning or deep learning or as well as NLP, that kind of all the possible combine effectively that gives some train model that gives some prediction output that we can also identify with the complex systems. So this is one of the image that with the help of AI. Generative AI is very the recent trends is the generative AI that generates the model of the produce text and that in the that is maybe available in form of the texts, images as well as in the form of the videos. So generative AI is a new approach or is a current approach. These are the two images that is generated with the help of generative AI. So some prediction, some output we are looking with the help of this after computation of these complex algorithms. But of course, there are limitation of this generative AI or AI that is a, we have a very limited trained data. Okay, so we are not getting all time all the data set to do our tasks. So that is one of the limitations. And also we are struggling with the real creativity. So you can see the by just looking this two image, we cannot 100% say that it's original image. So we are saying that it's a struggling with the true creativity as well. So lack of understanding of the many complex ideas, existing ones, difficult to adopt every complex task in terms of algorithms. And of course, data privacy and security is a major concern nowadays. Once we are playing with the complex or large data. So that limitations of the AI, generative AIs. That AIs also help with the IGN, the system that gives the frequency loss allocations for each cell in our cell phone. So that is done by the AI technology and that add with the quantum and AI machine learning approach that gives the cell's location where that cell phone is currently operated that we can easily find out. And based on that, we are doing the training of the data and then test the data and then use in the real environments. Also, so with this kind of input graphs, we can generate the different types of output graph like classical computations as well as quantum computation. You can see the difference in number of test point, a little less here as compared to this one. Here that number of computation points are larger. So if there is a number of computation points are larger, that means that kind of approach is more accurate as compared to by traditional quantum computing. So that way we can say that this limited trend data I can convert into the accurate conversations when I if I using the AI approach. With this result, I get more predictable response. Hybrid neural network is also one of the case where this kind of graphs are converted into number of large masses. So mass is nothing but that gives the number of runtime points in my system. So again, it gives the more accurate results with the help of this computing approach. So with these three technologies, there is traditional computing, then quantum computing, and the AI. That is our predictions or some performance of the task. So this all we have to use together, okay, that we call as a quantum AI. So in this diagram, we have a classical computations, we have a quantum computations, and we have a AI also. So in this white region at the center, this quantum AI come into the picture. So we have to use our traditional approach, that is our 0 and 1 approach, our 4-bit approach, that is our qubit approach for computations. And then finally, we need to generate some prediction also with the use of this computation. It's not like just we do the calculation and we have to stop at that point. No, after the computations, we need to predict, yes, these are my what I expect and that results are getting. That is my AI applications. So that application I have to develop with the generative AI or AI systems, and these all three combined together, that is my quantum AI approach. So there's a computation speeds are too high that at the time I cannot use the classical one because it is limited up to physical limitation. As I said that 1 nanometer, I cannot go beyond that. I have to use single electron. So in that case, quantum come into the picture. So I can do the quantum computing with the quantum hardware and I can develop the complex algorithms. Once it is there, I can use my AI model for the predictions. This all three together we call as a quantum AI. So this is the recent approach where artificial intelligence comes into the pictures with the traditional classical computing and the quantum computing. So yes, so quantum AI is that the use of the quantum computing with the machine learning algorithms because the traditional computing approach we cannot use for the high complex algorithms, supervised or unsupervised case. In that case, I have to switch my system level designs as well. And we can predict the many results that are not possible with the classical competence and with the help of the our quantum computing. So quantum AI is that a quantum computing and that gives the unique properties of quantum mechanics. So there is a once there is quantum is involved, that means there is a single particle rotating in multiple directions. And if it is there, we can perform complex computation in a less time. If my algorithm is also complex, yes, that is a based on the machine learning. I have to combine these two approach and we'll get the notation that we call as a quantum AI. Yes, computing power as the early 19th, as I said that limited number of transistors are there, but nowadays you cannot see even the transistor with your eyes. You require special microscope to see only the device. Okay, algorithms and everything is a software level. So I suggest all the university that you have to spend too much budget towards the hardware side because software available very easily nowadays. But you invest, they will purchase more and more hardware, so that actual implementation, actual realization is only on the hardware. So that your whatever your university budget you can utilize to purchase the hardware, maybe GPU or maybe this kind of computer system as well. So IBM only developed that in 2021, that quantum computing phase or that to develop to give the designs, and they are facing many challenges in terms of initial power level and the processing levels. This is the limited performance of our device that we almost reached the limit of the devices. We have a performance we call as a speed in technology. We almost reach, let's say, 3.4 gigahertz is the maximum speed of our laptop, not beyond that. So in that case, we reach the limited speed of device. Clock frequency also maximum. Power in terms of watt, 300 watts, and almost number of cores are also there. 10 number of cores, 15 number of cores. That cores is also at the saturation level. We cannot go beyond this limit. These are all numbers are saturated, and these are all to the key parameters for the computations. So what could be the next? So in that case, I have to use the quantum computing and I can go beyond this number. If I wish to 1 gigahertz, I can go for 1 gigahertz clock frequency also. If I want to reduce the power, definitely with the higher speed, I cannot reduce the power. There is a trade-off. So I have to use additional hardware to minimize this power dissipations. And of course, I can go with the large number of cores. There is a parallel processings. So we all know these terminologies. That is we have a BJT, MOSFET, CMOS. Many devices are there, but they are all not sufficient for the higher competitions. So at the last stage, in 1 nanometers, 2 nanometers, we have to use some carbon nano ribbons, carbon nanotubes, spin wave device, nanomagnetic logics. This kind of devices are very useful for the higher competitions. And latest one for quantum computing is this kind of quantum dot cellular automa. QCA is a device approach or hardware approach on this on that quantum computing is running. On that, we are applying our machine learning complex algorithms. Along with that, we can do the prediction of our systems. So quantum AI, there is of course the rise of AI. More than AI, okay, with the higher computational speed, we identify that as a quantum AI. It's a multi-core approach and the complex algorithm we can able to run on that systems. And yes, the quantum AI we call as a strong AI, a system, the artificial general intelligence. Yes, so this is our capability. As a human, we can do this all things. We can have a logical capacity, we have quantitative intelligence, okay. We have psychological intelligence, social, emotional, everything is all comes into our human intelligence. That is memory intelligence also we can remember short, can be medium or long-term memories also for the different tasks. So similar approach we are applying for our AI as well as computing AI. So we are looking this all these features, human intelligence features, we are duplicating in terms of equivalent machine approach. So this is possible with the help of quantum AI. So yes, quantum AI use this quantum computing approach, the hard and machine learning algorithms, and finally it develops the AI models. And in that case, it achieves the beyond capacity that solve the complex problems. So right now we are struggling with that 27 camera of the cell phone. How we are using that traditional approach of computing 0 and 1. So we are not able to do the processing of that all 27 camera at a time with the single CPU. So we are stuck at the three. We are reach up to the 3 nanometers, but not that project yet completed. So we tell to the customer that yes, we are researching on the new device, new approach. So we given the target them yes in 2027 that kind of cell phone available in market. It has a 27 camera in backside that do the processing at a time, take all the angle images, and with the higher computational model we can develop. So with that limitations of the our traditional system, but of course with the quantum AI, we can go beyond that limitation as well. So how this quantum AIs work? That this is all the inputs and this is the outputs at the right hand side. So initially it pick up the traditional database as our V1, V2, V3. That is our traditional database, which is converted into the quantum database. So traditional database is available only in terms of 0 and 1, but it is converted into multiple bits. That is our quantum data set with the help of traditional algorithms. And then we evaluate for each database or each inputs, we generate the quantum model. And then we take the average or sample of that model for individual inputs, and based on the complexity we can evaluate the classical model for that performance. So maybe that performance in or that model in terms of area, that model in terms of cost, everything that could be defined based on the requirements. So we have a this is the same picture over here in the different form where we take this traditional database and convert into the quantum database, and then we use the quantum neural network models to appropriate selection or sampling, and then we take the averaging of all the system to get the final cost model for our systems. So this all steps require high computations, which is not possible with the traditional computing. So these are all steps, as I said, that we use the conversions of quantum data to quantum data sets, and then we use the neural network models to perform the task, and we take the average because final outcome should be one complete model. So we cannot generate a different model for one same data set. So taking the average, taking the samples, and then we use the final form of the classical neural networks that gives the better approach of the learning. So what we can achieve with this quantum AI? In the case of healthcare, we can achieve 30 to 40% faster drug recovery. So that is possible with the help of this potential of the quantum AI. In finance, we can achieve 20% rise in the prediction accuracy. So most of the stock exchange in upcoming future with the use of quantum computing, finance at the 20% is increase is possible. Energy saving, that is yes, 50% improvement in battery designs. If you open your cell phone, okay, or if you open the laptop, big size is only the battery. Battery technology is not too much advanced. Biggest size is our battery. Okay, so nowadays in EV vehicle also the problem of battery technology is not too much advanced. All semiconductor, all the technology are very too much advanced, but this battery is somehow not become too much advanced. So that can be also reduced by 15% energy saving with the help of this quantum AI. Applications, we have many applications where risk assessment is there. Traditionally, it was in hours per day. Now it can be reduced to seconds or minutes. Portfolio optimization was a complex task. Now it can be become simplified also with the help of quantum computing. Fraud detection. So if now on our cell phone also that initial rings are coming like this. So previously it was reactive. Now it becomes pro-reactive. So everything we can optimize, which are somehow saturated nowadays with the help of quantum AI. So quantum AI, that is a, in short, we can say that is a more powerful quantum systems that can be used open source modeling and training platforms to design the complex algorithms. Substantial and skill developments that ecosystem can be developed. Yes, someone can mute yourself. Yeah, someone can mute, your organizer can mute them. We are compiling AI applications.
1 minute.
Yeah.
Yeah, okay.
Yeah, we are compiling the AI application for which you can do the quantum computing outcome. It's about classical computings. Okay. So these are all the benefits we'll get for the quantum AI. So why it is so important that because nowadays AI is a buzzword, but in upcoming days, the quantum computing and the computing AI that becomes the buzzword because so many predictions in that case of stock markets or in terms of medical, in terms of biomedicals, in everywhere there is a huge demand for higher speeds because data is increased day by day. So that at the same time, computational power need to be increased with the more accuracy. So whenever accuracy come into the picture, of course, we have use of AI models. So high speed with accuracy that combined together, we have a better quantum AI. So this is the one topic of quantum dot cellular automa. So as I said that where we have to use this all the quantum algorithms complexity, where we have to utilize. Someone can mute yourself. Someone can mute.
Yes, sir.
Yes, sir.
Done.
1 minute.
Done,
Yeah.
sir. You can
Yeah.
continue.
So this is the approach where we have to utilize our hardware, okay? Because this what we talk that is at the software side, complex algorithms, computations. So everything need to be finally goes into the hardware. So for this quantum AI and quantum computing, this is the approach that is quantum dot cellular automa is a QCA hardware approach is there where we can utilize that system for real time applications. As I said, networking chip, as I said, 27 camera cell phone. So where is my hardware? So the answer is this quantum dot cellular automa. So let's see what it is. So it's a novel approach. It's also called the single electrons device where we have only island or single dot is there that can be act as my complete transistor, that is drain, source as well as gate. So this is novel approach, is a research approach where we can use the single electron for complete calculations. So this replaced the traditional CMOS with the QCA technology. In the CMOS, we have many electrons to represent the functions, but here we only single electrons that defines my all the entire device. So that gives me the improvement in speed as well as lower density. Then there is a property of the device that we can use the different material to develop this quantum approach. Okay, so there is a single electrons, there is no any collision, so my speed becomes higher. There is no any barrier affect the my device, so it can easily move. So what was the recent trend that, as I said, that IBM use this quantum approach, but it's not commercial, it is for that research. 5 qubit approach was there and reached to the 53 qubits as a quantum processor, that is by the Google, and 5 qubit used by the IBM Q5. So there are recent quantum computing systems are there. So quantum dots is approach to handle this quantum dots like we have single electrons. It has a valence band, conduction bands, and when it travels, it releases the energy in form of the current conductions. So the size is very small, either 2 or 10 nanometers. With that 2 or 10 nanometers, that means our single device. And if that kind of many devices are there, we can form complete hardware for the GPU. So it has a multiple valence band as well as multiple conduction bands. Whenever electrons are travels, they can travel from this side to this side with there is some valence band to conduction band with the multiple layers. And when it travels, it's release the energy that is our maybe light or maybe electricity. So original it was traditional approach was a bulk. Now quantum dots are in a picture which are very small in size. Okay, if they are small in size, as I said, area is smaller. That means we have huge competitions. And there are the numbers that are available in 1 nanometer size. They are available in 2 nanometers, 4 and 6. This all this indicates that yes, this is my single device of this size. And to perform the energetic relation of this, all the dots, we have a all confinement regions are defined. Let us understand with the image. Yes. So this is 2D nano structures where only single wall is there between left and right. That is our carbon wall. If there's a one dimensions, we have two yellow wires between entire rotations. And if it is a zero dimension, that means it is free in all three directions. Something like this. Yes. The zero quantum dot, that means it can rotate in all three directions. 1D, that means it rotates only in one direction and free in two directions. Third is quantum wire, that is free in one direction and fixed in two directions. Direction it is movement. And finally, 3D, that means our quantum dot, that is free in all three directions. So quantum dot is a approach. Okay, it rotates in X, Y, Z, all three directions, and that gives the better computational speed. So originally a concept was in 1993, was in system was in terahertz, and it's a dots and tunneling of the dots. Yes, this is the case. So this is my single device where I have quantum dots also and the opposite electrons also. The connection between these two with the tunnel junctions. Okay, so when this dark travels over here, that means there is a movement of carrier. This dark travels over here, there is a movement of carriers. So we have electrons, that is single dark circle, and this white circle is our quantum dots. So if it is in this polarity, opposite polarity, it is identified as a logic 1. If it is in this polarity, it is identified as a logic 0. We call as a polarization plus, polarization minus. So logic 1 and logic 0 is look like this one. Okay. Previously, if you remember in our CMOS, we require NMOS and PMOS, complete device. Now here single dot I can represent as NMOS and PMOS. So I have quantum dot, I have electrons, as well as polarizations, and we can define the state also, as I said, logic 0 as well as logic 1. This is the 3D views of the quantum dot cells. There's a tunnel also, that is traveling mediums. There is electrons also, okay, and there is a quantum dots also. So if we phase like this, we have logic 0, that is -1 polarizations. If we phase opposite like this, different cells, we have logic 1, that is +1 polarizations. We can accommodate so many cell like this also. Okay, these are all the quantum dot cell that forms together, that gives the layer approach, layer 1, layer 2, layer 3, like that. So there is a traveling or movement of this electrons to over here, this electrons to over here. That means its polarity is changed from +1 to -1. So what kind of device we can develop? So all logical gates, because this is what we are doing at the end of the day. Whatever microprocessor, whatever GPU, CPU is our digital design. So inside that we have digital gates. So we OR gate, AND gate, all the sequential combinational circuits we can develop with the help of this QCA logic. We can develop the wire also. As I said, we are using optical in the traditional one. But now, instead of wire, we can use this QCA logic just to transfer the data from here to here. So my connection is performed like this. So whatever input and output are same, that means this is single wire. So I can use as a wire also to transfer the data. And all possible gates like majority gates as well as OR gate, AND gate, all possible gates I can design with this quantum cells. This is majority gates. This is very traditional OR gates. So this is my CMOS logic, but this is now quantum logic. Okay. On that, my quantum AI is working. So I can, with OR gate functionality, we all know that this is NOT gate. Okay. I can develop the NOT gate also, complements gates, NAND gate with the different polarizations selection. I can design possible gates. NOR gate also I can develop. Okay. All, if I know or plus NOR, that I can say it's a NOR gate. XOR also, all possible gates, even XNOR also. Only this is the biggest, that area compressions. Okay, I can minimize the area of my device, so my computational speed becomes higher. That is a major approach for this QCA methodology. I can go for more complex design like MUX, half adder, full adder as well. Okay, and as I said, using FPGA, CPLD, in ASIC, any hardware if you want to develop nowadays. If this quantum approach is there, we can develop that quantum computing, because at the end, that whatever complex algorithms we have to dump on that hardware, and that hardware is our this QCA methodology, QCA technology. So many challenges, of course, that latencies, power, energies, crossover minimization, because it is only single electrons transferring. So interference is also the major effect. And if you are in a university, this is an open source EDA tool available. Okay, there is a QCA designer. 3 versions are there. So you can give the students to in your BTech, or maybe even in case of MTech, UGPG levels, that open source tool that they can use to design the digital gates library. The software is QCA designer. It's freely available. You can design all the combinational sequential circuits, and you can feel that yes, my single electron can behave in a small area with this small power dissipation and in a less time, rise time and fall time. That simulation also you can visualize. So yes, we have the quantum AI applications, a number of applications there. Financial modeling, natural language processing. These are only few of them. Drug discovery. We can, whenever there is a complex algorithm with limited hardware, we can always go to the approach of quantum AI. Can use for solving the complex problems, higher efficiencies, of course, enhancing machine learning approach as well. So current challenges, design challenges, that quantum hardware. As I said, that we are at the 3 nanometer, but still we need to go 1 nanometer, and then quantum electronics will start. Also, the noise, error correction, as well as detections. Advanced algorithm need to be developed for classical applications. Of course, we don't have this accessibility of IBM and Google quantum systems. So we have they are only for their own research. So in a future of quantum AI, there is a rapid growth in the pattern recognitions, real-time optimizations, more accurate financial forecasts, okay, more possible ways where there is a complex algorithms are there, you have to apply the quantum AI. So this is the conclusion where yes, traditional computing as well as quantum combining with the feature of AI, artificial intelligence, we can reach to the quantum AI for the complex algorithm with the more accurate models. Of course, there are the challenges that need to be handled in terms of hardware. Mostly it is in hardware because software we can easily do, but when there is implementation point of view, yes, there is a design challenges. These are the references. Any questions, answers? Yeah, that is from my side.
Thank you so much, Dipesh sir, for
Yeah,
the nice presentation on quantum AI. Really, we come to know the plenty of new things about the AI after listening to you.
yeah.
Now, I request all the participants to ask the question if they may have.
So in a company, we are developing this kind of AI based approach also. So we have a complex systems are in it there with the client side requirements, and we first try with the traditional approach. If it is not there, we are going for the quantum approach, and then we apply our AI intelligence as well. So better prediction, better model we can develop for their end applications. So there is a one client that says that whenever flight is coming at the airport, every user have to wait for their luggage. Okay, so there is also find there is a solution available based on the AI and this quantum computing. So when there is they are on the way, the luggage is there with the help of that kind of approach. Algorithms are there, not need to be developed with the help of hardware. It is possible with the least time.
Yes, any participant have any further queries?
Oh, count is 239. So how many participants? 400 something, or this is
Actually, participants we have approved is 385.
okay.
And due to the some DT issue, some government participants are not allowed to participate as the DT has put restriction to
Mhm,
30 peoples only.
mhm. So today is the sixth day of this FDP, right?
This is 6 day of the epic.
And the time is 2 to 9, right?
Yes, today it's three sessions, 2 to
Okay.
3:30, 3:30 to 5, and 5 to 6:30.
Mm-hmm.
Then the students will have the examination on ATAL portal
Mm-hmm.
and then valedictory function for 30 minutes.
Okay. Sunday is also working tomorrow?
No, this is last
Yeah.
day.
Today is the last day. Yeah. Okay, fine. It was started
Uh,
on from Monday, right?
yes.
Okay. Very good.
Uh, Thank you, sir. As no participants have any queries,
Yeah.
I request Joshi sir to take the
Yes,
charge.
yes. Thank you, Dipesh sir. Just all participants and Dipesh sir, if possible, just if you switch on the camera for 30 seconds, then we'll take a one screenshot. Thank you very much.
Thank you.
Thank you, Dipesh sir,
Yeah, thanks a
for
lot.
the session, as well as uh, to all participants. Just one of our expert was not able to deliver the session because of some medical reason. Uh, we just requested InfoChips for arranging an expert related to this, and on the next moment they accepted our invitation. Thank you, sir. Thank you very
Yeah,
much.
thanks a lot.
Uh,
Yeah, my pleasure.
you may log out or you can stay, as now uh, we are going to invite our next expert,
Yeah,
Nilesh sir.
yeah. Thank you. Thank you. Bye.
Yes, sir. Yes, bye, sir.